Hi, everybody. In this video, I'm going to explain our work on similarity evaluations via sampling. This is joint work with my undergraduate student, Wang. Let me start with a motivating introduction. There are many applications where we need to perform a lot of distance or similarity evaluations, comparisons between complex objects. For example, we want to find the best match for a DNA sample in a database, or the best match for a fingerprint, best match for an image, and so on. Or we want to group similar objects into clusters. There are many situations where we need to this type of similarity search or this clustering. And to reduce the complexity of those tasks, there have been basically two approaches. One is to try to reduce the total number of distance or similarity evaluations by, for instance, exploiting the triangle inequality and organizing the objects in appropriate data structures. And the other approach, here I mentioned two examples of approaches that would fall in this second category, in which what you want to do is to simplify, to make the computation of the similarity measure or the distance measure more efficient. Maybe you just abandon the exact computation of the similarity and you use some estimation. In particular, we will focus in the cases where we need to evaluate the similarity of two objects which are or can be modelized as sets or multisets. As an example, we can consider long sequences of DNA, divide the sequence into groups of k consecutive letters. Those are called k-mers, and then consider the set or the multiset of distinct k-mers in the DNA sequence. Or our object can be a text, a document, and we can consider the set of distinct words, the multiset of distinct words in the text, and so on. There have been many different similarity measures defined in the literature, and we have identified almost 80. But here I'm giving a short list of measures that we have considered in this work. The most famous is the well-known Jaccard index, which is the ratio between the size of the intersection and the size of the union. The cosine similarity is also well known. It's actually the quotient between the scalar product of the two vectors that represent A and B divided by the product of the norms. Here you have several other well-known similarity measures. Now, our approach is, to estimate the similarity of two sets A and B according to some similarity measures sigma. We will take two random samples, SA and SB, from the two sets, and then our question is the similarity of the two samples an unbiased estimator for the similarity of the original sets? If not, can we sort of correct, make some change in the computation so that from the samples we can infer we can derive an unbiased estimator for the similarity of A and B. Finally, how accurate are those estimations? How do they depend on the size of the samples? Because, of course, the larger the samples, the more accurate the estimations will be, right? That's quite intuitive. Now let me move to how do we sample. If we want to produce samples of fixed size, this is what you can find in many places in the literature. Basically, you will be hashing all the elements in your stream or your set, and you will keep the elements such that the hash value is among the k largest hash values, or the k smallest, doesn't matter. So the invariant here in this loop is that you keep at all times in your sample the k elements with the largest hash value. But, and the fact that under some assumptions, reasonable assumptions, like there will be no collisions, distinct elements will not hash to the same value because, well, if we pick enough bits for our hash functions, the probability of collision is negligible. And also, we can assume that those hash values will be essentially random. Therefore, the set of k elements with largest hash values, smallest hash values, is essentially a random sample of size k. Every element, every distinct element in the set, in the stream, has the same probability of being sampled. In this work, we propose to use the affirmative sampling, which was formalized 2 years ago, although the algorithm is around already for a while. And in affirmative sampling, what we have is a small change so that it guarantees that when the larger the cardinality is, then the larger the samples will be, at least on expectation. So in this sense, the samples represent better the diversity of the set. And as before, all distinct elements have the same opportunity to be sampled. That's the reason for the name of affirmative sampling, because of those two properties. And essentially, in affirmative sampling, the only difference is this line, this part. So when an element has a hash value that's larger than the k largest value in the sample, then we make the sample grow. We add this element and we make it grow. So the sample at any moment will have this structure where you have the k elements that have largest hash value, and in this case your element will enter here and the sample size will grow by 1, right? But when an element is in this region with hash value below the k largest, but still larger than hash value that is larger than the minimum hash value in the sample, then this element gets kicked out and your element enters the sample. And what happens then is that the size of the sample is a random variable, and it's exactly the number of k records in a random permutation of size n. And this is something that we know very well how it behaves. The sample does not contain the k records. It contains a certain number of elements, and we are sure that those elements are those that have largest hash value. Therefore, that's a sample, a random sample of that particular size that it has. Okay. And the size of the sample can be used itself to estimate the cardinality, the number of distinct elements in the stream or in the set, and thanks to this estimator, which we call recordinality. As I mentioned, the size of the sample is a random variable that's very well known, very well understood, and in particular the expected size of the sample will be k log of n divided k. We also know well how the number of times that those replacements where an element in the sample gets kicked out and another one enters the sample, but the sample does not grow. And the number of times this happens, this Fn, we know the expected value and the variance, and this allows us to carry out the average case analysis of the cost of affirmative sampling, where you have this term that corresponds to scanning the stream, and in many cases, basically you will be discarding the element because the hash value is too low, or you will be updating the statistics because it's an element that you already have sampled. And only in those cases you will be adding some element to the sample or making a replacement, and that gives you the average cost of affirmative sampling. Now, once you have been able to produce samples of from random samples from your sets, you can estimate what's the proportion of elements in the set or in the stream, distinct elements, that satisfy some property, P. You want to satisfy the ratio, and what you have to do is to compute the same ratio in the sample. How many elements in the sample satisfy the property divided by the total size of the sample. Now this S is a random variable, and we have, this is a well-known result that this is an unbiased estimator, but we have proved that, we have made sure that this is also true when the size of the sample is itself a random variable. And we have carried out the same the analysis for the variance of this estimator. And it's given by this expression where the expectation of 1 over S gets involved. And in the case of affirmative sampling and also of variance of affirmative sampling, this behaves asymptotically as 1 over the expected size of phase. Now, to estimate the Jacquard similarity and other similarities, what we will be doing is we collect the two samples from A and from B, and those samples are the elements in A whose hash value is above some threshold, and the elements in B whose hash value is about some other threshold. So if we take the largest threshold and we filter the two samples according to this threshold, which is the largest of the two, what we get is a random sample from A union B. And the intersection of your samples is giving you how many elements in this sample satisfy the property of being in both A and B. And therefore, applying our theorem before, what we get is that the expected value of the similarity between the two samples, once you have filtered them, is the similarity of A and B. And applying the other result, we have also the variance. And as you see here, now we make this variance in the estimation go to 0 as long as the size of the union of the two sets, when the two sets grow larger. Okay. We can use those samples also to estimate the size of the intersection, not just the ratio between the size of the intersection and the size of the union. No. We can use the samples to estimate the number of elements in the intersection. Here you don't need to filter the sample. You perform this computation, and which is giving you the ratio. And then multiply by, well, it's essentially an estimation of the cardinality of A. You can do it with the recordinality or with the famous K minimum values estimator, which involves the threshold, and those two estimators are unbiased estimators of the size of the intersection. The same proof that I have sketched for the Jaccard index also works for other similarity measures, and in particular also for the containment index that is 1 when A is a subset of B and 0 when they are totally disjoint. The expected value of the containment between the samples is an unbiased estimator of the containment between the sets. For Jaccard, for Simpson, for Brown-Blanket, Kulczynski 2, Sorensen dice, the result holds that the unbiased, the similarity of the samples, once you have used a common threshold to filter them, is an unbiased estimator of the similarity of the sets. And we conjecture that this is also true for other similarity measures, in particular cosine, correlation, and Kulczynski 1, which are the measures that I have mentioned in my list before. Here I'm showing you a few experiments that show here, for instance, the spread that we get in the estimations performing 100 elements. The black line is the true similarity in the similarity measure, the Jaccard index. The red one is the average of the 100 experiments. Yellow one is giving you the standard deviation. Now here we have two sets, and we can sort of make the intersection grow, and then this makes the corresponding similarity measure change. The red line is the Jaccard index for A and B, as we range the size of the intersection from 0 to 1000, and the blue dots correspond to the estimations, and the bars to the standard deviation. And you see that happens for Jaccard, but for Sorensen's dice, for the Sorensen dice coefficient 2, for the Brown-Blanket, for the Simpson coefficient, Kulczynski 1. It turns out that for this measure we don't have the proof that is an unbiased estimator. However, the experiment suggests that it could be the case. Here the spread is much larger because of this denominator that goes to 0 when the two sets are very similar. Kulczynski 2, cosine also, which is not, for which we have no formal proof that is an unbiased estimator. It seems that it is, and for the correlation ratio coefficient 2, we have also this kind of plots where we have plotted the theoretical value of the standard error, which is the standard deviation divided by the expected value, as given by a formula in our theorem and as given by the experiments, and there's a very good match between the two. And this is a bit amazing because if we apply the same thing for this estimator, which is not proved to be an unbiased estimator of the similarity of the cosine similarity, and we don't know what's the standard error for this similarity measure. However, it seems that applying the same, if we conjecture that the estimator is unbiased and we apply the theorem, we get also a pretty good match here too. This leads us to a conjecture of this type, that the standard error will behave as 1 divided by the square root of the similarity, divided by the square root of the similarity and the size of the sample. And since we are using affirmative sampling, this size of the sample will grow, and this allows us to make the standard error go to 0 as we cope with larger sets. Some final remarks. We want to prove those conjectures for many other similarity measures, for the similarity measures for which we haven't been able to prove it yet, like cosine and Kulczynski one. Also the conjecture for standard error, and to carry out a similar analysis for multisets. We have already some preliminary results for the Jacquard index in multisets, and the thing is that you cannot sample elements with distinct sampling, but you have to give more weights to frequent elements. And that's it. Thanks a lot for watching. You know how to locate me, to contact me. If you have doubts or comments, they will be welcome. Thank you very much. Bye.